Welcome to G Fun Facts Online. In an era defined by digital precision, we're facing a colossal and largely unseen crisis: the immense energy consumption of artificial intelligence. As AI models grow more powerful, their demand for electricity is skyrocketing, posing a significant challenge to global energy grids and sustainability. The International Energy Agency has highlighted that electricity consumption from data centers, AI, and cryptocurrency could double by 2026. This surge is a formidable environmental problem, but in a surprising twist of technological history, the solution to this very modern crisis might lie in the past. Scientists and engineers are turning back the clock, finding inspiration in an 80-year-old technology that predates the digital revolution by decades: analog computing. This once obsolete approach is experiencing a remarkable revival, promising a future of AI that is not only powerful but dramatically more energy efficient. The digital infrastructure that underpins our modern world, particularly the data centers powering AI, is incredibly energy intensive. These facilities consume 10 to 40 times more energy per square foot than typical commercial buildings. Globally, data centers and their transmission networks account for a staggering 1 to 1.5% of all electricity use. The advent of large-scale AI, especially generative models, has exponentially increased this demand. Training a single large AI model can be astonishingly costly. One study estimated that this process could generate over 626,000 pounds of carbon dioxide equivalent. The reason for this immense consumption lies in the fundamental architecture of digital computers. Modern digital processors, based on what's called the von Neumann architecture, separate their processing units, the CPUs and GPUs, from their memory units. AI computations, especially the matrix multiplications central to neural networks, require the constant shuttling of vast amounts of data back and forth between these two points. This data transfer creates a traffic jam known as the von Neumann bottleneck. This bottleneck not only slows down computation, but, more critically, it consumes a tremendous amount of energy. In fact, this data movement can increase energy use anywhere from 3 to 10,000 times more than what's needed for the actual calculation. This isn't just an item on a tech company's balance sheet. It has real-world environmental consequences. The increased electricity demand strains power grids, which are still heavily reliant on fossil fuels, thereby increasing carbon emissions. Before the world ran on ones and zeros, it ran on waves and continuous signals. This was the era of analog computing. The concept is ancient, with early examples like the Antikythera mechanism from ancient Greece using gears to model celestial movements. In the 20th century, electronic analog computers, which emerged during World War II, used physical properties like voltage and current to directly represent and manipulate data. These machines were adept at solving complex differential equations and were instrumental in fields like aerospace engineering, used for everything from designing jet engines to guiding missiles. However, with the dawn of the digital age, analog computers were largely relegated to museums. Digital systems offered superior precision, programmability, and the ability to store vast amounts of information without degradation. But now, the very limitations of digital computing are prompting a second look at its predecessor. The key advantage of analog computing for AI is its incredible energy efficiency. Instead of the constant, power-hungry switching of billions of transistors to represent binary code, analog systems perform computations using the natural physical properties of their components. This approach can be up to 1,000 times more energy efficient than digital methods. The most revolutionary aspect of this revival is a concept known as in-memory computing, or CIM. In this paradigm, the distinction between processor and memory blurs. By performing calculations directly where data is stored, analog AI chips can completely eliminate the von Neumann bottleneck. This not only saves immense amounts of energy, but also dramatically speeds up computation. The heart of the analog AI revolution lies in how it handles the math of neural networks. Deep learning models rely heavily on a calculation called a matrix vector multiplication. In a digital system, this involves retrieving huge matrices of numbers, the weights of the neural network, from memory and multiplying them with input data in the processor. Analog AI chips reimagine this entire process. They use arrays of components, such as programmable resistors, whose physical properties can be set to represent the weights of the neural network. When an input, represented as a set of voltages, is applied to this array, the resulting currents are instantaneously calculated according to Ohm's law and Kirchhoff's laws of circuits. The output is a direct, physical computation performed in parallel and in place. This brain-inspired approach is a cornerstone of neuromorphic computing, a field dedicated to creating hardware that mimics the structure and function of the human brain. The brain, after all, is the ultimate analog computer, processing vast amounts of information with remarkable efficiency. Several key technologies are enabling this transition. At the forefront is phase change memory, or PCM, a technology also found in rewritable CDs. Materials in PCM cells can be shifted between crystalline and amorphous states by applying electrical pulses, which changes their electrical resistance. This allows a single memory cell to store a continuous range of values, not just a 0 or 1, making it an ideal synaptic cell for storing neural network weights and performing computations. Similar technologies like resistive random access memory, or RRAM, also use changes in resistance to store information, offering another path to efficient in-memory computing. A diverse ecosystem of established tech giants, innovative startups, and academic institutions is driving this analog revival. IBM Research has been a major force, developing prototype chips that use PCM technology and can perform AI tasks with an estimated 14 times more energy efficiency than comparable digital hardware. One of their recent chips, built on a 14-nanometer process, contains 64 analog in-memory compute cores and integrates both analog and digital components to achieve high accuracy. This proves that analog AI can match the performance of digital systems for tasks like speech and image recognition, while being significantly faster and more efficient. Mythic, an Austin-based startup, is another key player, focusing on bringing high-performance, low-power analog computing to edge devices like drones and smart cameras. Their analog matrix processor uses compute-in-memory with embedded flash memory to deliver massive parallel processing. The company claims its technology can provide the performance of a desktop GPU at a fraction of the power. For example, Mythic has showcased chips running complex object detection algorithms on high-resolution video at 60 frames per second while consuming only 3.5 watts of power. Other innovators include Rain Neuromorphics, which is developing chips that mimic biological neural networks, and researchers at MIT who have developed analog processors using protonic programmable resistors that can process information 1,000,000 times faster than previous designs. Despite its immense promise, the path to a fully analog AI future is not without obstacles. One of the primary challenges is precision and noise. Analog signals are continuous and can be affected by environmental factors like temperature, which can introduce errors. Digital systems, with their discrete ones and zeros, are inherently more robust. Another challenge is programmability and scalability. Designing and manufacturing analog chips is a more complex process compared to the well-established digital workflow. Because of these limitations, the immediate future of AI computing is likely to be a hybrid one. Many of the most promising new chips, like those from IBM, are mixed signal systems. They combine the strengths of both worlds. They use analog cores for the massively parallel, energy-intensive matrix multiplications and digital circuitry to handle tasks that require high precision and to correct for any analog noise. This hybrid approach harnesses the speed and efficiency of analog without sacrificing the accuracy and reliability of digital. The revival of analog computing represents more than just a clever engineering solution. It marks a potential paradigm shift in how we approach computation. As the physical limits of Moore's law for digital chips become more apparent, analog AI offers a new path for innovation, one that prioritizes sustainability alongside performance. By drastically reducing the energy consumption of AI, analog technology could make advanced artificial intelligence more accessible and affordable, unleashing a new wave of innovation. The environmental benefits are equally profound. Greener AI could significantly reduce the carbon footprint of the tech industry and help align the rapid advancement of artificial intelligence with global sustainability goals. The journey is still in its early stages, but the 80-year-old principles of analog computing, once consigned to the history books, are now powering some of the most advanced research on the planet. This unexpected comeback story is not just about reviving old technology, it's about reimagining the future of intelligence itself, a future that is faster, smarter, and, crucially, more sustainable. Thank you for tuning in to Fun Facts Online.